What's up? We're here today to talk about some standing sound waves. So we actually just finished talking about standing waves on a string, and there's a really good visual with that with using a simple harmonic oscillator and your frequency generator, and we did that with those standing waves on a string to see all this area of constructive and destructive interference. Now, standing sound waves are actually very, very similar to this concept. And before you watch this video, there is actually also a demo of me playing with some boom whackers. And we'll talk in this section a little bit of the consequence of those and how, especially how they relate to instruments. And I talk about open, and open, closed tubes. Well, we're going to talk about that today. So what is a standing sound wave? Well, in the demo, I used a boom whacker because it's an enclosed tube, but it allows pressure or air, I should say, to kind of like slosh back and forth. So right here, we got a nice little picture of this. When we have at one instant, we have an area of compression, which we know represents a area of high pressure, and an area of rarefaction, which represents an area of low pressure. So the air molecules, they're oscillating, creating these compressions and rarefactions, and as they're going back and forth in the tube. So we have it when I hit the tube, there's an area of compression that goes, and that causes an area of rarefaction, and those are kind of sloshing back. So a standing sound wave is when those waves that are traveling, they eventually reach the end of the tube. So if I were to draw a little tube, I don't know how good I can draw a tube, but I'm going to try. So there's my tube. It's very straight. Inside the tube is what's happening inside the tube, but when we're outside the tube, we have some air. So that is some discontinuity. So inside the tube, there's going to be some change in pressure. Outside of the tube, we have atmospheric pressure. And we talk about that a little bit when we get into fluid dynamics. But the air molecules are sloshing back and forth, and all of a sudden they reach the air molecules of their environment, which causes a discontinuity in mediums. And we talked about discontinuity way earlier on when we talked about like when we're going from one medium to another medium. So when that happens, part of the wave's energy is transmitted, meaning it goes into the new environment, out into that new pressure, which allows you to hear the actual sound, but part of it is actually reflected back into the tube. And that causes these molecules to slosh back and forth, pushing against each other and pulling apart from each other, causing these areas of compression and rarefaction. So some of the air molecules leave the tube and hit your ear, and some continue to slosh back and forth. And then maybe the next time that molecule gets to leave the tube, or the energy from that molecule, I should say, not the molecule itself, but the energy from that molecule gets to go into the medium and eventually hit your ear. So we can break these types of tubes into a couple different types of tubes, and what's interesting is the consequences of those. So if we have just a basic tube, which is how I started the demo, this basic tube is open at each end, so it's called an open tube. Now, how this is visualized actually varies depending on who's teaching it. So our textbook, I enjoy the way they do it, but with an open tube, we're assuming that each end of this tube has a node, and the one complete wave is going to be inside of that tube. Or we can even have even more than one complete wavelengths. But the antinodes are going to be inside the tube where it has the greatest pressure. So I could also have a standing wave that's very simple, and that's going to be that guy right there. So I have nodes at either side. This is visualizing what's happening in the tube. And then I have antinodes inside the tube. And that's where there's going to be maximum compressions and rarefactions occurring. So a standing sound wave is when we have air molecules in tubes that are closed at one end or both ends, and they'll rush out, creating this compression and rarefaction. and therefore a closed end of a tube is going to be an antinode. So if I imagine now, here's my open side and my closed side, we're assuming that this right here is going to be an antinode. So with those couple things in mind, we can start visualizing the waves that are going to occur in open-open and open-closed tubes. So here is what open-open and closed-closed tubes can look like, and open-closed tubes. So in a tube that's open at both ends, we're going to have antinodes in the middle and nodes on the outside. A tube that is closed at an end, whatever end is closed is going to have an area of antinodes, and it could be closed at both sides or just closed at one side, as we see with an open closed tube. So the way we visualize this is with those rules, we can regulate exactly what that wave is going to look like as it's standing inside of the tube. So this first line here, this first group of pictures, all represent a mode number of m equals 1. Now, that's the first standing wave that we get, and we can get more and more standing waves. Now, with open and closed tubes, we can have mode numbers of any whole number integer. But with an open closed tube, since we have to have this antinode on this side and a node on the open side, we actually only get every other integer, so only odd number integers. So I can have m equals 1, 3, 5, 7. So my mode number can only go up every other. Now, the other interesting thing is this mode number of 1 on the closed is actually only a quarter of a wave. So that's all we see, right? Well, in order for me to have a complete wave, I didn't draw this too great, but I actually need 4 times the length of that tube. So open closed tubes are actually what we utilized in the determining the speed of sound lab when we had tuning forks and we were playing them above the air column, and we found that resonant frequency, and I said you had to take that pitch or take whatever the length was and multiply it by 4. Well, this is why. It's an open closed tube. Now, with an open tube and a closed tube, when I have an open tube, this is a half of a wave, so the actual wavelength is twice the length of the tube when we have a mode number of 1. It is the length of the tube when we have a mode number of 2. And that's the same thing we talked about when we got into standing waves on a string. So I got a quick check here, and the answer is already up there. Oops. Here we have an open tube has a mode number of 3. Well, that means I will have 3 bumps. So there's an antinode, and an antinode. With an open closed, I have to have an antinode at that wall. So if it's a mode number of 3, well, it's not 3 bumps. And remember that a mode number of 3, that this length actually needs to be 4 times that length. So if it was a mode number of 3, I'm actually only going to have 1.5 bumps because I need to multiply that times 2 to get my mode number of 3. So the mode number is a little different for an open closed tube as it is for an open tube. So we do come up with some frequencies or some equations then similar to the standing waves on a string. So if we have an open or a closed tube, our formulas are identical to standing waves on a string. And I have that fundamental wavelength is twice the length of the string divided by mode number. So that is absolutely identical. When we get into an open closed tube, then it's no longer twice the length, it's actually 4 times the length. So the only difference is that I'm using 4 instead of 2 as my multiplier, because an open closed tube acts like a tube that is twice as long as an open tube. And that's what you should have seen in that demo. So a quick little summary. Here is everything for, we have our standing waves on a string. We have our open and closed tubes. And those all have the same formula. But then we also have an open closed tube, which is slightly different than all of the other ones. Now, there are some interesting consequences when dealing with standing sound waves, especially as it relates to your hearing capabilities. So, one random interesting little thing is that you actually have different perceived loudnesses based on the frequency of the pitch that's being emitted. So, you actually hear different frequencies even if they have the same sound intensity being put out or the same power being put out, you actually hear different frequencies at different intensities. So low frequencies, you guys actually hear pretty loud and pretty easily. But higher frequencies, even though, like when I use the frequency generator on my computer and I put up a higher frequency, it was playing at that same volume, but it seems softer. It's not as loud as the lower frequencies were. You can play around with that. Set your, again, go to Google and type in frequency generator, set your speakers to a set volume, and put in like 50 hertz or 100 hertz, and it'll seem really loud. Then put in 2000 hertz. And yes, it's painful, or it can be painful and a little bit more intense, but it seems quieter. So it's a weird consequence of standing sound waves as it relates to your ear canal. Now, I mentioned this in the demo before this video, but getting into this concept of wind instruments. So a wind instrument is anything that uses air to play. And if I think about, this is like a very simple early variation of a flute. And flute is a wind instrument. It's a woodwind, right? So a flute or any wind instruments use holes to change the length of the tube. So if I think about going back to, I don't know, let's talk about a saxophone. When I play a saxophone and I put buttons down, as I start to push those buttons down, I make the instrument longer and longer. Now, our fundamental equation is that velocity equals frequency times wavelength. So as I push more buttons down, so right here on this picture, think of the hole as like the first time the sound can come out. Now, the more holes I push down, here was my initial wavelength. Now from this one to when I have 3 holes down, here's my next wavelength. So as I make that wavelength longer and longer before it can release or come out, the velocity stays the same. So my frequency is going to get shorter or lower and lower, meaning a lower pitch. So when I have wind instruments, I push buttons down, and therefore I make them longer. Now, some of you might say, well, what about things like trumpets? Well, trumpets actually work exactly the same way. A trumpet has valves, and those valves open up other areas for that wind to flow, which does increase the length of the instrument. The only exception are instruments that fall under the category of an open closed tube. So right here, these tubes are open at both ends, right? Now, a clarinet actually falls under the category of an open closed tube. And some of the evidence behind that is actually thinking about the relative frequency of a clarinet. So if a clarinet's playing, it's actually a very low sounding instrument. It's a very low pitch compared to a saxophone, which is a little bit higher of a pitch. But the clarinet's a smaller instrument. Because of the concept of wind instruments, the shorter the instrument, the shorter the wavelength, the higher the frequency would normally be. But clarinet gives you a very low frequency with a shorter tube because it's an open closed instrument. Another consequence of that is when you get into the concept of the overtone series. Again, your mode numbers for an open closed are only every other mode. So a clarinet only can hit every other overtone. And if you don't understand anything about overtones, don't worry about it. So here's a quick little example problem, and that example is warming up. So wind instruments, they have an adjustable joint that changes the tube length. So a clarinet, for example, is actually a couple pieces of an instrument that gets put together. A saxophone has a neck, and then at the end of the neck is cork, and that cork then you put your mouthpiece on the cork, and that is how you adjust that frequency of your instrument by changing how long it is to make it be in tune. So to examine this, let's take a look at what happens when we warm up. Now we know that warming up is important in band. Many of you use it as an opportunity to talk to each other. That's not good. To warm up literally means you warm up the inside of your instrument by pushing air through it. And that dramatically changes the frequencies that that instrument is going to be playing, because the air temperature velocity is dependent, the velocity of sound depends on the air temperature. So far we've just said, oh, velocity of sound, well, let's just call that 340 or 343 meters per second, whatever. Doesn't really matter. We're going to assume that it is 343 meters per second. Now, the actual formula, if you're a nerd like me, for the velocity of sound through air is actually 330 meters per second plus 0.6 meters per second times the temperature in degrees Celsius. So every degree Celsius that your instrument warms up, that causes the velocity of sound to increase by 0.6 meters per second. So it's crazy, right? Just by warming up my instrument, I am speeding up the speed of sound in the instrument. Well, who cares? Well, velocity equals frequency times wavelength. If my velocity goes up and my wavelength stays the same, my frequency will also go up. So as I warm up, I get sharper and sharper. So I need to account for that as I am playing an instrument. So long story short, let's go all the way back to what the point of this problem is. Let's take a look at a cold flute, warm up, and see what happens. So at 20 degrees Celsius, I have a cold flute. The speed of sound is 343 meters per second. That my flute, to play the correct 440 hertz A, I need my flute to be exactly 39 centimeters long. So I adjust the flute, I adjust the joints in the flute. If it's a trumpet, it has a tuning valve, same thing with trombone. I adjust the length of the instrument for it to be exactly 39 centimeters. Now, as I warm up, as I blow air through the flute, we're going to assume that we go from 20 degrees Celsius all the way up to 32 degrees Celsius. Well, as I do that, I actually increase the speed of sound. So as I increase the speed of sound, I was at 343 meters per second. Now I'm at 350 meters per second. So my new frequency that I'm playing with this increase of velocity, because remember, frequency is going to be velocity over twice the length. My new velocity is 449 hertz. Well, I was supposed to be playing 440. Now I'm playing 449. So now I am out of tune. I am sharp because my instrument has now been properly warmed up. A consequence of that, we'll actually finish off this unit by talking about beats. And that's the last section, that's 16.7, I believe, is beats. And we'll talk about that later. So in order to account for this instrument now being sharp, I need to change its length. So using my new frequency of 449 hertz, my new speed of sound of 350 meters per second, I can determine the length of my instrument as being 39.8 centimeters. So it wasn't much, it was about 8 millimeters. But those 8 millimeters are going to dramatically make my instrument out of tune. So I need to adjust the instrument. So when you're sharp on an instrument, you pull out. So I make my instrument slightly longer. How much longer? Literally 8 millimeters longer is all I have to make my instrument, but that'll make it in tune. So that's actually it for standing sound waves. Now the next section is actually a little random. We're gonna talk about some of the consequences of speech and hearing, but then we'll get into a little bit more about sound waves interfering with one another. So we'll see you in the next segment.